This lesson, we're going to learn about geometric sequences. Let's remember, we've learned about sequences before being a pattern of numbers, but we've learned about arithmetic sequences before. Maybe something along the lines of like 2, 5, 8, 11. This would be arithmetic, where we had what we called a common difference. And that common difference was I'm adding 3 each time, right, to get from one term to the next. When I add 3, we were able to say, hey, d is equal to 3, and we had a formula, an explicit formula to write these, and we said that was our first term plus n minus 1 times d, right? So if it was arithmetic, it was when we were adding or subtracting a common difference or adding a negative common difference instead of subtraction. With geometric, we have a different type of pattern that's occurring. With geometric, that pattern that's occurring is through multiplication. And instead of a common difference, we call it a common ratio, and that's our R value. Okay, so we can determine if it's arithmetic, geometric, or neither by first looking at, well, is there something that we're multiplying by or adding by to get from one to the next? So for example, here in example 1, from 21 to 63 and from 63 to 189, just in terms of number sense, we're adding a lot more in the second round from 63 to 89. So I'm adding 42 here, and then I'm adding 126 here. So those aren't the same. So the arithmetic is off the table. There's not a common difference. What I then can figure out is like, okay, is there a common ratio for us then? So I can go across and say, all right, is 21 times something 63? If I don't know that answer off the top of my head, what I could always do is I could say, well, if I'm saying if is 21 times, we'll say is there a common ratio? Is 21 times r equal to 63? We can divide both sides by 21 to try to solve for r. And so we can take 63 divided by 21 in our calculator and say, all right, that's 3. Okay, this is multiplying by 3. Well, it's 63 times 3, 189. 63 times 3, is that 189? Great, it is. All right, let's check just to make sure. Is 189 times 3, 567? Yes, that's great. Awesome. Right, so each time I'm multiplying by that r value times 3 to get from one term to the next. It's geometric with an r value, a common ratio equal to 3. In example 2, we can do the same thing. So we can see like, okay, switching from positive to negative clearly means like, hey, I'm increasing, I'm adding something here, and then going from positive to negative here, now I'm subtracting something. So quite clearly, it can't be an arithmetic sequence, but it actually told us, hey, it's a geometric sequence. So there is an R value. There has to be, right? Because it's telling us for a fact there's a geometric sequence, meaning there's a common ratio. Okay, so let's find the common ratio. I can do that by doing the same thing I did over here to the side with 21r is equal to 63, I can take any term and divide it by the term before, right? Because any of these terms, like negative 1,215, I would multiply by r to get to my next term, 405. All right, let me divide both sides by negative 1,215. So we can take that 405 divided by negative 1,215, and we can find that we're multiplying, let's use our exact value of negative 1/3. That's our r value. So r is negative 1/3. So if I want to find the next 3 terms, we have 45. Let's take 45 and multiply it by that negative 1/3. And then multiply that by negative 1/3. And then multiply that by negative 1/3. And we can find our next 3 terms. We have negative 15, 5, and negative 5/3. So the alternating pattern actually of negative, positive tells us automatically that our R value has to be negative, right? Because if R was positive, we wouldn't change signs. The negative by multiplying by negative is what's flipping signs here. So looking at some of these as a little bit more basic, determining if it's arithmetic, geometric, or neither, we're looking at, are we adding, are we subtracting, are we multiplying, dividing, or is there no pattern at all? So for number 1, I'm looking at, all right, it's not arithmetic because I'm adding 1, I'm adding 2, all right, arithmetic's off the table. But instead, what I can look at is like, all right, is this multiplication? Yeah, what a pattern I'm seeing is that I'm multiplying by 2 each time. So this is geometric because of the fact my R value, my common ratio is 2. In 4, I'm taking a look and saying, all right, I don't see anything like multiplication pattern, but let's check arithmetic. I add from negative 2, I add 7 to get to 5. I add 7 again to get to 12. I add 7 again to get to 19. So since I have addition here, This is arithmetic because our common difference, d, is equal to 7. If we're being told in the next section that we have a geometric sequence, this tells us for a fact these are geometric. That means I have to find my R value, my common ratio. Again, to do that, I can take any term and divide it by the term before, because it's multiplication going from negative 648 to negative 216, or 648 to negative 216. So then it would be division to go backwards from negative 216 to 648, right? So multiplication this way, but it'd be division this way. So I can take any of them. So I'll go further down in the sequence. I can take 72, divide it by negative 216. To find my R value, and again, similarly as before, we have our R value is negative 1/3. So to find my next three terms in the sequence, I'm going to go to 72 then, multiply that by negative 1/3, and I'm going to rinse and repeat and continue doing that, multiplying by my common ratio, negative 1/3, each time, negative 24/8, and negative 8/3. Good. So for the next one, we're going to do the same thing here in 6. We're going to say, like, all right, what am I multiplying by? And you might be able to see it, how I'm decreasing. So my R value here, or like at least like the absolute value of what I'm decreasing in. So like from 25 to 5, I can think about like, all right, to go from 25 to negative 5, my R value has to be negative. But we can always use that trick in the calculator and say, I'm going to take any term and divide it by the term before. So we'll try, let's take negative 5 and divide it by 25. And our calculator will rotate this out. We can use the decimal or the fractional approximation or fractional value of this. So we can get negative 1/5 as our R value. To find the next three terms then, I'm just going to take that 1. Well, 1 times anything is whatever we're multiplying the 1 by, so we know it's going to be negative 1/5 as our next one, right? So I can take negative 1/5 and multiply by our R value, which is negative 1/5. To get 1 over 25 and multiply that by negative 1/5 to get negative 1 over 125. So big thing, geometric sequences have a common ratio, right, that we can find. That common ratio we're multiplying by to get from one term to the next. So then we had also talked about explicit sequences for arithmetic. We're going to talk about explicit for geometric as well, that we can find any term n, the nth term, in any geometric function by saying it's a sub 1 times r to the n minus 1 power, where a sub 1 we've talked about here before is my first term. And then we have our common ratio r that we've been using so far. So writing a geometric sequence for the nth term here, we need to figure out two things. What's our first term, which we have, and what's our common ratio? So we have our first term is 5, and then we're thinking, all right, what am I multiplying by to get from one to the next? This one's a little bit more simple, but we can use our calculator trick if we want to, because we know 5 times 4 would be 20. 20 times 4 is 80, and so forth and so on. So to write that equation to find the nth term, that means all I simply need to do is take that explicit formula above and plug these in. This is 5 times 4 raised to the n minus 1 power is my answer. Then it says find the seventh term of the sequence in B, and that's n is equal to 7. So I'm going to plug in n is equal to 7 to calculate this. Yes, we can do a little bit of simplification of 7 minus 1. This is 5 times 4 to the 6th power, which in our calculator we can handle. To say 20,480 would be our seventh term. Here's our answer. So again, bringing that explicit formula down, right? Our explicit formula is that we're going to take our first term, multiply by r raised to the n minus 1 power. N minus 1 power. Okay, so again, we need to identify a couple things. What's our first term? And then what is our common ratio? So our first term should be very obvious because that should come straight from here. All right, and then our common ratio depends. We can use our calculator, or if I know what negative 2 times what is 10, because we're told this is a geometric sequence, this gives us a common ratio of negative 5. So I can plug that in for my R value, and here's what it asks us for first. Then I can turn around and say, what's the 11th term? I can find a sub 11 by plugging in n is equal to 11 and get negative 2 times negative 5 raised to the 11 minus 1 power, or negative 2 times negative 5 raised to the 10th. And we can go straight to our calculator to do that. Negative 2, careful with parentheses, times negative 5 raised to the 10th power. And we get negative 19,531,250 as the 11th term. And the next one, very similar. We're going to start by first finding the explicit formula by taking our first term, 512, multiplying it by our R value. All right, so a little bit harder. You may not know what 512 times what is 128. So just like we've done before in this lesson, we can take the 128 and divide it by 512 to go backward and say, all right, what's my R value? That's 1/4. So I can then get 1/4 as my R value here, raised to the n minus 1 power. Sweet, there's my explicit formula. Now to find the sixth term, I'm plugging in n is equal to 6 into my explicit formula. A sub 6 is equal to 512 times 1/4 raised to the 6 minus 1 power, or 512 times 1/4 raised to the 5th. And then we go straight into our calculator. Close my parentheses. We are putting the 5th power on this, and we get 1/2 as our sixth term of that sequence. So the last thing in this lesson is going with recursive formulas. So just to review recursive formulas, something that we did before with arithmetic sequence, recursive notation means that we're using terms before it, or terms that precede it, right? Precede means before. So we talked about this before, where when we did recursive formula, we had this subscript notation like a sub n minus 1. And we said that means one term before. And the one specifically coming from, and we had given examples, but the one specifically coming from that one right there. If I did a sub n minus 2, which we won't in this class, but that would mean 2 terms before. So essentially we said, look, recursive formulas give you a definition based off of terms before, but they also need to define a first term. So we're finding the first 5 terms of a sequence, and guess what? We were given the first term. That's what this tells us here. That's negative 4. So now I need to find the next 4 terms. But I also can just read my rule right here and say, look, what is this saying? This is saying 3 times 1 term before, or 3 times the term before. So to find my next term in my sequence, to find my second term, I'm going to take my first term and multiply by 3, and I get negative 12. To find my third term, I take my term before, my second term, multiply by 3, I get negative 36. And we can keep doing this, so we can take negative 36 and be like, all right, to get my next one, I just multiply by 3. Get my next one, multiply by 3, and keep going, but I don't need to keep going. Negative 108, negative 324. Those are fine. Those are my first 5. So for 14 here, again, we're defined here with our first term. That's 5. Great. That's awesome. But what does our recursive formula tell us? Our recursive formula says negative 2 times the term before, or 1 term before. So I'm going to take 5 and multiply it by negative 2 to get negative 10. I'm going to take negative 10, multiply by negative 2 to get 20, multiply by negative 2 to get negative 40, multiply by negative 2 to get 80, right? It's just the same exact idea as the geometric sequence. It's just written in a different way. It gives us a starting point, it gives us our first term, and then it gives us a rule. So to write these things, we have 2 more problems here. To write these things, writing recursive formulas, you need 2 things. You need to define the first term. My first term is 5. Then I need to define my rule. I need both of those things for a recursive formula. So my rule is going to be what on the term before? How am I going to get from one to the next? So I don't think about adding in this case. From 5 to 15, I would add 10, but from 15 to 45, I'd add 30. So it's not an arithmetic rule. Instead, from 5 to 15, I multiply by 3, multiply by 3, multiply by 3. My rule is multiply the term before by 3. That's our recursive rule right there. So in 18, again, with recursive, start off always, let's define our first term. And now we need to define what's happening to the term before. So this one's a little bit more difficult. All right. So we can look at this and be like, all right, it's definitely not subtracting the same thing over and over again because those differences are too large from one another or too different from one another. But instead, I could take any of these terms. I could take 81 and divide it, right, by 243 and say, all right, is that a multiplication factor? All right, that's 1/3. Let me check. Let's make sure it's the same all the way around. Let's take 27 divided by 81. And let's take 9 divided by 27. Right? They're all the same the whole time, which tells me that common ratio, that rule is, hey, I'm going to multiply the term before by 1/3.